Hello, welcome back. Today we're going to talk about Newton's law of gravitation. This is part one. So in the beginning, I'd like to describe Newton's law of gravitation, where it comes from. We want to also talk about how it fits into the other forces in the universe and learn a little something about how special gravity actually is. Then we'll solve a problem to get our hands dirty, so to speak. But mostly this is a general lesson to try to get you to understand Newton's law of gravity, what I say, in your bones. In other words, have an intuitive feel for what the equation says. So you're not just plugging stuff in, you're actually understand what all of the different parts of Newton's law of gravity is. Now, before we actually get to Newton's law of gravity, let's take a big picture, right? There are, as far as the current theory of physics goes, four forces in the universe. Every force that you have ever talked about, either in a physics class or even just in everyday life, can be explained by one of the four fundamental forces of the universe. Today we're talking about gravity, which is one of the four, but there are three others that I'm going to touch on because I want you to have the big picture. And the big picture thing that I want you to pull away from this is that gravity, the one that you feel like you have the most experience with, is actually the weakest of all of the other forces that we know about in the universe. And not just a little bit. Gravity is millions and millions and millions of times weaker than any other force in nature. And that's something that surprises a lot of people when you hear it because we're stuck to the ground, we feel gravity and so on. Now, we're going to talk a lot about that and convince you that in fact it's not just a little bit weaker or maybe a million times weaker. Gravity is many, many, many tens of millions of times weaker than any of the fundamental additional forces. So before we jump into Newton's law of gravitation, which I promise we're going to get to very soon, I want to give you the big picture. There are four fundamental forces of nature. Of course, there could be another theory that comes along tomorrow and adds another force to this list, but right now, as far as we know, everything in the entire universe can be explained by one of these four forces. First, we have the strong nuclear force. I'm going to talk about it in just a second, but it has to do with the nucleus of atoms. Next, we have the weak nuclear force. All right, so these are both nuclear forces. Next, we have the electromagnetic force. Right? This is electricity and magnetism, which you typically learn as two different forces, but actually we know electricity or electric force and magnetic force is really part of a single force called electromagnetic force. And then we have wimpy little gravity at the bottom. Right? And when I say it's weaker, it is many, many, many tens of millions of times weaker. So this is the weakest of all of these four forces. Now, this is not a class in nuclear physics, right? I just want to take 2 or 3 minutes so you can appreciate what we have learned. We, being collectively humanity, with our tiny little brains, have managed to figure these things out through experimentation. All right, so the strong nuclear force, the top one on the list, it's, as you might think, it's the strongest of the four forces. When you think about it, you know that this force, the electromagnetic force, you can have electric repulsion and electric attraction, right? So when you think about it, in the nucleus of all the atoms, you have the protons, right? You also have neutrons that don't have any charge. We have the protons, which are positively charged. But you learn that this electromagnetic force, or this electric force, you want to think of just an electric force, two positive charges should repel each other. So the nucleus of all these atoms are full of positive charges. And even as a kid, I wondered, well, why doesn't the nucleus just explode? Well, the nucleus is always trying to explode of every atom, even my skin, everything. It's trying to explode all the time. But it turns out that there is a deeper force inside the nucleus, not related to electricity or magnetism, called the strong nuclear force, right? The details of how it arises goes into the theory of quarks and such, and that's what protons and neutrons are made of. But we're not going to get into that here. There is a deeper force that's much, much stronger than electricity or magnetism that actually holds the nucleus together, even though the positive charges are trying to blow the nucleus apart. That's why it's much stronger, and so it's called the strong nuclear force. Without the strong force, there would be no atoms at all, of any kind. Any atom, calcium, magnesium, none of them would exist, okay? In fact, if you make the nucleus too big, physically large, right, where the strong nuclear force cannot reach out and grab onto it, because even though it is the strongest force, it is a very short range force. It only acts over very, very tiny distances, the strong nuclear force. So if the nucleus gets very large, like in uranium, right, or plutonium, or any of these radioactive elements, then the strong force has a hard time holding the nucleus together and the nucleus begins to fall apart. We call that radiation. So if you have a radioactive element, particles are coming out of it because it cannot be held together very easily. Even with this strong force, the nucleus is just too big. So large elements at the bottom of the periodic table, they have a hard time staying together. We call them radioactive. So that's the strong nuclear force. The weak nuclear force, I'm not going to get into the details, but it has to do with radiation. The weak nuclear force is involved in when one particle turns into another particle. There's a weak, we call it a weak nuclear force, which is involved in that process. So it's all happening inside the nucleus as particles decay and so on. And then you have this electromagnetic force. So two magnets repelling, two magnets attracting, we call it magnetic forces, but we also have electric forces. Positive charges, repel, opposite charges retract. Electron and a proton, for instance, will attract each other. So we used to think that electricity and magnetism were separate forces, but actually we now know they're unified and all part of a single force called electromagnetism. And in fact, we can make disturbances in the electromagnetic field, and we call those electromagnetic waves disturbing the field, and we call that radio waves or microwaves or gamma waves or whatever whatever you want to talk about. But any disturbance in electromagnetic field, we call it photons of light. We call it light. That's what we call it, or radio waves, right? It's all the same deal. But anyway, all three of these are many, many millions of times stronger than wimpy old gravity. That's what we're talking about here. Gravity has the distinction of only being attractive. It's only attractive, whereas electromagnetism can be attractive or repulsive. And in fact, electromagnetism, specifically the electric forces between electrons and such, are the entire reason that chemistry exists. So any kind of chemical reaction, burning something, any kind of chemical reaction in your body, turning food into energy, releasing heat, releasing energy, anything where a chemical reaction is taking place is involving the electrons changing positions in the compounds you have. All of that is due to electric forces. So it's all wrapped up in this electromagnetic force. When your muscles move, you say, well, what force is that? Well, that is a chemical reaction inside my arm, right? So that is an electric force. Electromagnetic force is what governs that. You might say, well, what about when I push on the board? What force is that? Well, the resisting that I feel is from the flexing of the board, and that's the attraction between the atoms, and those are all electric forces, right? When I sit in a chair, the chair is pushing up with a normal force. Where does it come from? It comes from deforming the material of the chair, and it springs back. Those are all electric forces. So actually, most of the forces that you experience in everyday life, other than standing on the ground from gravity, they're always due, or almost all of them are electric forces. Any pulling on a rope, pushing on a couch, any of those, kicking a ball, those forces are all basically microscopic electric and magnetic forces. Gravity is the odd one out because it's only attractive, and gravity can act over a very, very far distance, right? So we're going to learn what the equation predicts, but what we're going to know and just kind of think about is that according to Newton's theory of gravity, every object in the universe that has mass is attractive to every other object in the universe. So this pen is attracted to my head. This pen is also attracted to the board. The board is attracted to the pen. The board is attracted to my head. The pen is attracted to the camera. The pen is attracted to the sun. The pen is attracted to Alpha Centauri, 4 light years away. This pen is also attractive to another galaxy, many millions of light years or hundreds of millions of light years away. Every object is in attraction with every other object in the universe, right? Now, it gets weaker, the force gets weaker as things become separated, but the attractive force is still there according to Newton's law of gravity. Now let me just stop for a second and say that the point of science really isn't to know the truth, right? We always want to know the truth, but in reality, we know that we may never know the real truth. What we really try to do is build better and better models of reality that predict reality better and better. And the better and better you predict reality, then the better we say your model is. Is the model really truth? Like, is it really work according to Newton's law of gravity, for instance? Well, no. We know that Einstein came up with a better theory of gravity. It's called the general theory of relativity, and his theory of gravity involves curving of space and time. That gravity maybe is not a force, but maybe it's a geometric folding or bending of space and time, right? And it turns out that Einstein's theory of gravity is much more accurate when calculating things than Newton's theory of gravity. So we think that Einstein's theory of gravity is much closer to the truth. But we also know in modern physics that we have quantum mechanics. And according to quantum mechanics, which does not include gravity, everything else is, it comes in chunks. Like a photon of light comes in a chunk. We call it a quanta of light, a single particle of light. Electrons come in little chunks, little single chunks of matter. Protons, quarks, everything seems to come in chunks. That's called quantum mechanics, right? So maybe gravity should come in some chunk. Maybe there's a particle of gravity. Maybe gravity should be folded into quantum mechanics like everything else. And so scientists are working on that, and we do not have a unified theory of gravity. We do not have a quantum theory of gravity. But if someone makes a model of a quantum theory of gravity that predicts things better, then we will think that that is one more step closer to truth. So, knowing that Newton's law of gravity is not as good as these other theories of gravity, is it worth studying? Answer is yes, it is absolutely worth studying for a couple of reasons. The reason we study Newton's law of gravity is because it allows us to solve problems that are not so difficult, and you can learn a lot from them. Number two, even though it's not as accurate as Einstein's theory of gravity or other theories of gravity, it is perfectly fine to make calculations with Newton's theory of gravity that are accurate enough to send a spacecraft through the solar system, for instance. So even though it's not as good, it is good enough to send space probes to other planets. It's very useful, much easier to calculate. It took Einstein 10 years to develop his theory of gravity. So if it took Einstein 10 years, then the mathematics is difficult enough that it is very difficult to do simple calculations with. So we always start our journey in physics learning about Newton's theory of gravity. We use it, but then as you continue your studies, you'll learn about other theories of gravity, which are a touch more accurate, but also much harder to apply. The mathematics is much harder. All right, so that's a ton of talking, okay? I just wanted to give you the big picture before we get into it. All right, now, one thing I'm going to say before I write the equation on the board. Gravity is the weakest of the four fundamental forces of nature. Let me give you an example of how it's so weak, all right? This body of mine is attracted to the ground with a gravitational force. I'm being pulled into the ground. Now, the Earth is really big. The Earth is huge, and I'm just a tiny little speck standing on the top of it. And every particle of matter in the Earth is attracting my body down. The entire Earth, through the gravitational attraction of every atom in the Earth, is what is holding my body down with whatever I weigh, 160 pounds, 170 pounds, whatever it is, of force acting in the downward direction. But if I spring my legs up and down and just apply a force, I can break free of the theory of the force of gravity momentarily until it stops me and it pulls me down. So I can jump, right? So gravity we think of as very strong. But actually, it's so weak that the entire planet pulling on my body can be overcome by my simple little legs. And my legs are powered by muscles, and my muscles are powered by chemical reactions, which is all governed by electric forces, because any chemical reaction is electrons moving around in substances. So when you think about it, this electric force is so much stronger than gravity because the tiny amount of mass in my legs can overcome the force that the entire planet is exerting due to gravity. Now, the upshot with gravity is that it applies over vast distance scales. So we can have enormous collections of mass in galaxies and solar systems and nebula. And so when you add up all the gravity, it can get quite strong over far distances. But over smallish distances, it can be demonstrated how weak it is by simply jumping off the ground. I can overcome that force there. All right, so now it's time to talk about Sir Isaac Newton. Certainly one of the most intelligent, brightest, gifted people to ever have lived. If you ever read about his life, it's amazing reading about his accomplishments at such a young age, okay? So the story goes that he was sitting under an apple tree and watching an apple fall and hitting the ground, and also looking at the moon in the sky, and wondered, could the same force that pulls the apple down to the ground, could that same force extend all the way up into space and be applying that force onto the moon? And if that's the case, could that be an interaction between the Earth and the moon that allows it to go and orbit the sun, or orbit the moon to orbit the Earth? Could that same force that governs apples close to the ground stretch out into space and govern the motion of the planets? That's the question. So there were a lot of people back in that time, about 300 years ago, plotting the positions of the planets and monitoring them. And they figured out that all planets are actually in elliptical orbits about the sun, elliptical orbits. Most people think orbits are a circle, but actually the planets orbit in an ellipse, with the sun at one focus of the ellipse. And you learn about ellipses in math class and algebra class. But an ellipse is basically an egg-shaped orbit, and the sun is at one of the foci of the ellipse. So Newton asked himself, if the force that's pulling on the apple is the same exact force that's pulling on the moon, and if we know the shape of the lunar orbit is elliptical around the Earth, and we know that the Earth is elliptical orbit around the sun, which is very controversial, but if you take that to be true, what must the force equation look like to produce an elliptical orbit? That's what he worked on, right? He said, what must the mathematical form of the gravitational force be in order to produce a motion around the body that's orbiting as an ellipse, not some circular or some other, because there's many mathematical shapes. There's parabolas and hyperbolas, and there's circles and lines and all kinds of things, but we're saying it forms an ellipse. So what must the form of the equation of gravity be in order to produce an elliptical orbit? And he crunched through it and figured out this is what it must look like. And so we'll just reveal the punchline. If you have a planet over here, or some body, anybody, could be anything, and another body over here, and this body has some mass, we call it M2, could be the Earth, let's say, and this mass has a mass, or a body has a mass M1, and we're drawing circles here, but these bodies could be any shape, right? Then, and if these bodies are separated by some distance r, you could call it distance d if you want, whatever, call it whatever variable you want, then there is some gravitational force that exists between them, right? We know that this body is attracted to this one, and so we draw a vector pointed this way, and we call that a force of gravity F sub g, and we put a vector bar on top of it. And then we know also that this one is pulling on this one, so there's a force that way, but this body is also pulling this way, like this. And that's also called F sub g. Now, I've tried to draw the lengths of these arrows the same. I may have not succeeded, but they're attempting to be the same exact length. Because it turns out that the force that's exerted on this planet pulled that way is exactly the same as the force on this planet pulled that way. They're called F sub g, right? Now, I'm going to talk a whole lot more about why those forces must be the same, but it comes down to, remember Newton's laws. For every action, there's an equal and opposite reaction. So if you pull one direction, if they're interacting through a force, then the forces have to be equal, and they have to be acting on the opposite body, basically. We'll talk more about that in just a second. But there's a mutual attraction between these two. And if you were to let them go, then they would drift towards each other until they finally collided, right? And Newton figured out that this equation that governs this force must look like this. It must be the following. F sub g must be some gravitational constant, capital G. This is different than lowercase g that we've been using. 9.8 meters per second squared, that's a different number than this. This is capital G, multiplied by the mass of body 1, then also multiplied by the mass of body 2, but then divided by the distance between them, but not just the distance between them squared. This is the famous Newton's law of gravitation. And through experiment, which we're going to talk about in just a second, determined experimentally, we can calculate the value of G. And so we know what this universal constant is. It's 6.674 times 10 to the negative 11, and it has some crazy looking units. It's Newton multiplied by meters squared divided by kilograms squared. All right, what does this mean? First of all, he calculated that the force of gravitational attraction between two objects is the product of their masses, but then divided by or inversely related to the square of their distances. So, and this whole fraction here is just multiplied by g, but g is just a number. Don't get so freaked out like by the units. It's got some units, okay, but it's just a tiny number, right? It's a small number, 10 to the minus 11. It's just some number. It's a constant of proportionality. In other words, he figured out the form of the equation by saying, okay, we know the planets go around the sun or around the earth in this shape, this elliptical shape. We know the mathematical shape of an ellipse. Let's say that that shape is governed because of some force of attraction to the planet that's involved. What does that force of attraction need to look like mathematically to trace out that elliptical shape? And when you work through that mathematics, the equation that works is an inverse square law, is what it's called, where it's proportional to the two masses multiplied together but then divided by the distance. What this means is, if I increase the mass of this planet, then the force of gravitational attraction goes up. That makes sense if there's more mass, right? If I make this bigger, then I'm multiplying, I get a bigger number on top, and I get a bigger force if you hold everything constant. If I increase the mass of the other object, then same thing happens. I make this bigger, and then the force of gravity is bigger. But if I make them farther apart, then the denominator gets bigger, but not just bigger, it gets bigger squared. So if I make the distance twice as far apart, then basically down here it'll be 2 times the original distance, and when you square it, 2 squared is 4, and so if I double the distance, I'm going to be dividing by 4 on the force. So if I double the distance, my gravitational force is 4 times weaker. 4 times weaker because if I put a 2 down here, like double the distance, 2r, 2 squared is 4, right? So if I double the distance, I cut the gravitational force down by 4 times. So you can see that the stars that are very, very far away, they are attractive, but they're so far away that those gravitational influences are so tiny on us, we don't feel them. Now, a couple additional things I want to say qualitatively before we jump into solving a problem. I want to talk a little bit more about this because we really have to, I want you to get very comfortable with this, right? So we said if we increase the masses of the bodies, gravity go up. We said if we increase the distance between the bodies, gravity goes down, but it goes down by the square of the distance. We have this constant of proportionality out here called the gravitational constant. Notice the weird units here. If you put these units here, okay, let me ask you, what are the units of mass? It's kilograms, right? And the unit of mass here is kilograms, right? And the unit of a distance is meters, so this is meter squared. So on the top here, with forgetting about the g, it's going to be kilograms times kilograms is kilograms squared, and then it's going to be meters squared right here. So you have kilograms squared on the top, and you have meters squared on the bottom. We want the unit over here to be newtons, right? Because it's a force that you're calculating. So the units of this g have to be like this. They have to be meters on the top to cancel with the meters on the bottom. Meters squared on the top to cancel with the meter squared on the bottom. And it has to be kilograms squared on the bottom here in the unit to be canceling with the kilograms squared on the top here. So that the only unit left when you do the multiplication is going to be newtons. So that's why we say the units of this g is so weird looking. It's because the units have to cancel to give you newtons at the end. That's all it is. So don't get so worried about things like this. Right now, one misconception that a lot of people have, even me when I first learned this, is that, when you have like a planet and you have like an astronaut, the planet has like a really, really big mass, and the astronaut has like a really, really small mass. And so you think that the gravitational force on the astronaut from the planet is going to be like big, and you think that the astronaut pulling on the planet is going to be really, really small. But actually, according to this diagram here, you see you have the same amount of force pulling on this tiny little mass as you do pulling on the other mass. Because this gravitational force, it's not telling you like a one-sided force, one thing pulling on another thing. It's predicting the mutual forces acting on two different bodies. Let me say that again. The gravitational force equation from Newton's law of gravity, it's not predicting one force or another force, it's predicting a pair of forces. So what it's saying is the mutual force, Fg, that exists between two different bodies is proportional to all this stuff when you multiply and divide and multiply, and you get a final number. But Fg that you calculate, it's not like a one-sided thing. It exists as acting on both bodies. And you might say, well, that doesn't make sense. The Earth is very, very large. It should pull harder. And the astronaut's very, very small. It should pull smaller. But you have to think in terms of action-reaction pairs. Remember back to Newton's law of motion. Every action equal and opposite reaction, but those forces always act on opposite objects. The action-reaction pair, they act on the opposite, basically they're due to two forces between two bodies, and they act on the different bodies. So if my hand pushes on the board, that's a force acting on the board. The reaction force is the board pushing on my hand with equal and opposite force, right? But notice that those two forces are acting on different objects. I have one force acting on the board, and the reaction force is the board acting on my hand. Those two forces act on different bodies, but it's the same exact magnitude of the force acting on different bodies. Another example might be, if this is anchored to the ceiling, let's say, and it's rigid, and I'm gonna pull down, right? I'm gonna pull down. I have a force acting on the ceiling. Well, through this rod, I'm pulling. It's a pulling force. I'm pulling down so that I have a force acting on the ceiling. The reaction force would be the ceiling pulling up on my hand. But those two forces are acting on different bodies. One of them is my hands pulling on the ceiling, and the other one is my ceiling pulling on my hand. They're acting on the opposite body. So action-reaction pairs always act on the opposite body on a two-body interface or a two-body interaction. And it's exactly the same thing with planets. It's like there's an invisible string here, and although it's a little different because there's nothing there, and they're kind of attracted to each other like this. So the string would get loose, and it would just kind of like shrivel up and such. So it's not really the same thing. But to get the idea, since it's a mutual interaction between two bodies, you have one attraction acting on this body, and then the other attraction is acting on the other body, but the forces themselves are the same. It's very, very important for you to understand. All right? Now, you might ask, well, if that's the case, why can I feel the force of the Earth, but the Earth doesn't feel the force of me? Well, actually, let's talk about that a little bit more. Let's say that you had a situation with Earth, and then over here you had some astronaut just in space, right? Obviously, the mass of the Earth is much bigger, that's what the double arrows mean, much bigger than the mass of me, the astronaut. I'll go ahead and put my little smiley face right there. Mass of the Earth is much, much bigger, but according to Newton's law of gravitation, the product of their masses, in other words, Newton's law of gravitation doesn't just say, hey, look at the bigger mass and tell me the force. It doesn't say, look at the smaller mass and tell me the force. It says the product of the masses is what's important. The multiplication of the two masses. That means that both masses determine what the gravitational force will be, not one or the other. Even if one's much bigger, it's the product of their masses that matters. So Earth is very, very large, I'm very, very small, but it's the product of their masses, and divide by their distance here. And so there is a gravitational force right here called Fg, and there's a gravitational force right here, same length of the vector arrow, called Fg. The forces are the same, but they're acting on different bodies and they're acting in opposite directions. All right? Obviously, if you let them go, they're gonna come float together. Now, if I'm in orbit, I may try to orbit around. We're gonna talk about orbits later. But if you're not in orbit and you just let go, then I'm going to slam into the Earth. Now, you might say, well, okay, but the astronaut is gonna be the thing that moves. The Earth is not gonna move. The Earth is not gonna like float up to me, but actually, think about it. This is a force of gravity acting on the Earth. This is a force of gravity acting on the astronaut. But if you remember, right, from Newton's law, force is equal to mass times acceleration. And force is equal to mass times acceleration. What I'm saying is that this gravitational force would be acting on the Earth. So I can say Fg, right? And this gravitational force would be acting on the human, Fg, right? But the mass here is huge. And the mass here is tiny, 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 right? So if I have a very large force and I divide by something small, I can get a large acceleration. But if I have the exact same force acting on the Earth, the mass is so big, if I divide by m, like if I just say, well, what is the acceleration going to be? It's going to be the force of gravity divided by the mass. But the mass of the Earth is huge here. So the acceleration of the Earth is so tiny, I can never ever see it. But over here, the acceleration of my body is the force of gravity divided by my mass, but my mass is very, very much smaller, and so my acceleration, I can actually see it. So the bottom line is, as I stand here on the ground, right, the Earth is pulling down on me, and I am pulling up on the Earth, and we are pulling on each other with the same exact force. but just acting on opposite bodies. The Earth is pulling down on me, and I am pulling up on the Earth. But if I get to a stepladder and jump off, I'm going to see myself move. I'm going to move so much faster. The Earth technically will be moving up to meet me, right? That's what I'm trying to say. If the Earth is like right here, and I'm like, right, I'm about to fall down to the Earth, right? And I jump off a stepladder. Well, all we really see is myself falling down, but actually I fall down and the Earth comes up just a little bit. Why does the Earth only come a little bit? Because the acceleration of the Earth is so small you can't even measure it. And the acceleration of my body is so much bigger than that's all I ever see. But people think that the Earth isn't moving, but actually it does respond to gravitational influence, of course. But the mass of the Earth is so big that this tiny amount of gravitational force isn't going to really move it at all. So we just treat it as stationary, is what I guess I'm trying to say. So let me read my notes, make sure I got everything. Every object attracts every other object in the universe. If you have multiple forces acting on an object, multiple gravitational forces, then you add the resultant force up vectorially. In other words, Earth is acting on me, and they're producing these forces right here. If I draw the moon over here, right, then the moon is attracting me like this, and I'm attracting the moon, right? But also the Earth is attracting the moon, right, like this, and the moon is attracting the Earth like this. So you see there's all this interaction of forces going on. And if I want to figure out like what is the net force acting on me, then I have a vector here of a force and a vector here, which is another gravitational force, and I would have to add those vectors up mathematically to figure out how I'm going to move and what direction I'm going to move. And if you had many, many bodies, like in a solar system with many planets, then it's very difficult to calculate without a computer how something is going to move, because you can see the interactions are many-fold. If you let the system go, then what's going to happen first? Am I going to start moving to the Earth? Is the moon going to start to move to the Earth? And then once things move to a new position, all the forces then become different again with different arrows, and then you have to do the whole calculation again once things start moving. So we call it the three-body problem in physics or in aeronautical engineering, astronautical engineering. When you calculate how a satellite's going to move through the solar system, it's quite difficult because there are many, many bodies involved and lots of forces. All right, now last thing I'm going to say before we solve our actual problem or talk a little bit more about the next topic is I want to talk about the idea that this Newtonian theory of gravity looks like this. And I don't want to save the interesting things for many, many months from now. It turns out that the gravitational force, the Newtonian gravitational force of attraction, looks like this equation, right? But actually it has exactly the same form as the attraction or repulsion due to electric forces. Later on, we're going to learn that the Coulomb force, which governs attraction of electrons and any charged object, looks like this. It looks like another constant called K, that's just some electric constant, right? Instead of mass, it's the charge Q on the first particle, the charge Q on the next particle divided by the distance between them squared. Now look at this equation. I don't care if you ever solve a problem on this right now. We'll solve problems with this later when we talk about electricity and magnetism. But look at the form of the equation. It's a constant times two things multiplied together. In this case, it's the charges. Like if you had an electron here and a proton here, you'd have the electric charges there, right? And then you divide by the distance between them squared. It looks exactly like gravity. It's a different constant. And instead of charge, we're multiplying the masses together. But it's so incredibly interesting to me that this equation for gravity looks exactly like this equation for electric attraction and repulsion. It just goes to show you there are a lot of symmetries in physics and some similarities that we say, for instance, gravity obeys an inverse square law, and electric attraction and repulsion also obeys an inverse square law. Just something I wanted to point out. As we get into electricity and magnetism later, we're obviously going to explore this and solve a lot of problems with this there. Okay. Now, a couple of things as we solve problems. Right here, I've drawn a ball here and a ball here, and I said there's mutual attraction between them, the force of gravity. Now, it turns out that when you're talking about outside of two bodies, the two bodies are separated physically, then you can treat the problem as if their entire mass is concentrated at a point. And that makes things very easy, right? Now, let me show you what I mean by that. Let me go, I guess I'll just do it I guess I'll just do it right here. Let's say we have right here Earth, and over here we have Moon. And they have some masses, some enormous masses, right? Well, we can treat the Earth as if it were concentrated at a single point. And we call that the mass of the Earth, but not as a distributed sphere, as just at a single point. And we can treat the mass of the Moon at its a single point. We call it the center of mass of the Earth and the center of mass of the Moon. And this will be the mass of the Moon, right? And so instead of drawing arrows on these big objects, we can just treat it like this, and we can say there's a force here and there's a force here. We call this Fg. We can call this Fg like this. Now, why can we do that, right? Well, it gets into actually a little more complexity than I want to get to here. But I'm just trying to tell you, it's not an assumption that's just like a cheat. It actually is possible to treat the extended body as being at a singular mass at a single point. Mathematically, it's true. You can use calculus to show that the gravitational attraction due to an extended body like that, like, in other words, if you looked at every single particle on the Earth and drew a line to the Moon, and every little particle was attracting the Moon separately due to gravitational attraction, and then you concentrated the mass here, you can show through calculus that because of all the different angles involved, you see how my angle is up high and then my angle is up low? When you add it all up using calculus, you can show that you get exactly the same force if you do it that way than if you just concentrate the mass at the center of the object. So you'll see a lot of times I'll say, hey, there's a planet over here and there's a planet over here. Tell me what the force is between them. And the first step will be, well, I'm going to put a dot for the planet and a dot for the planet. That's because that's a theorem that you can do that mathematically and it's okay, right? So when we talk about the distance r between objects, this r, it's not between the surface as I have drawn it here. The distance r between them, really, notice how I drew it to the center of this object and I drew it to the center of this object, because the distance r is really between their centers, because their center of mass would be concentrated in the center there, like that. So if the objects are separated, then you can treat them as point objects at their center of mass with the mass that they have. Now, I want to, before we do our first problem, talk to you about, well, what happens if we start to dig a hole in the Earth and we have like an extended massive body? What does gravity look like as you start digging down and going inside the Earth? Does it get stronger? Does it get weaker? What does it look like? All right, so let's take a look at what is going on inside the Earth. Inside the Earth. And what do I mean by inside the Earth? I'm saying, let's take a situation like this. The Earth is really, I think I'm going to do it with a black. The Earth is really, let's say, this big. Right? There it is. That's an extended body in space. It has some center and it has some radius, okay? Now, let's say that I dig a tunnel and I want to figure out if I dig a tunnel, let's say, to here, and I have a pebble right here. I'm going to put a pebble right at the bottom of my tunnel. Right? So literally, I dig a hole in the ground, and the hole has a bottom to it, right? And it's very, very deep. You see how deep I am compared to the planet. So maybe I dig, 1,000 kilometers down or 500 kilometers down or something like that, and then I put a pebble at the bottom. What is going to be the gravitational force on the pebble? Is it going to be higher? Is it going to be lower? What do you do? Well, it turns out that you use exactly the same gravitational equation as we have used before, but what we use for the mass is not the whole mass of the Earth in that case. What we do is we kind of take a spherical object at that depth right here. Basically, for the purpose of the calculation, this is the mass that counts. So I'll put right here, this mass counts. So if I dig down, and I know the mass of the particle, that's m1, m2 is not going to be the entire mass of the planet. It's going to be the mass of a sphere at that depth right here. And it would be like concentrated. That mass would be like concentrated at a point here. And then it would have two particles. So this particle will be attracted downward just like before, but not with as much force. So as you start digging down, you're going to weigh less and less and less because of this phenomena here. Now, you might say, well, why does the mass of the attraction only depend on, a tiny little sphere inside of the Earth at this depth? Why is that? Well, if you think about it, if you're standing here, what force of attraction are you going to feel here? Forget about what's going down here. you're going to have attraction with all of the particles on the other side of the planet over here. I'm going to be attracted down due to those, but all of the particles that are up here is going to be pulling me up. You see, because when I'm standing down in the bottom of the tunnel, I'm going to have mass below me, but I'm going to look up, I'm going to have a lot of mass above me. I'm going to have a lot of mass above me too. And that mass above me, not just directly above me, but way over to the sides, right? All around the planet is going to be pulling me up. So if I stand here and look up, I'm going to be pulled upward and then eventually pulled kind of to the side. But then this mass down here is going to be pulling me down. And it turns out that the upward pulling over here of all this mass and the downward pulling of all the mass over here exactly cancels out. And you can show that using calculus. All right, so let's go a little deeper, and I do mean that quite literally. Let's dig a deeper hole and see what happens there. We can learn a lot by these little thought experiments here. What happens if I have the same planet, but instead of digging a hole that deep, I dig a hole, let's say this deep. Very, very deep hole. And down at the bottom, you know, I can put my little pebble or whatever it is down there. All right, well, what's going to happen in this case? Actually, let me make it a little bit, maybe not quite so deep. I think I got a little bit carried away there. Make it a little bit shallower here. What is the gravitational force on a pebble once we go into the planet? Something like this. Well, it'd be the same thing. If the center of the planet is there, then the mass that's going to matter is going to be a sphere that's inside of that depth, basically this mass. And I'll draw a little arrow here like this because this mass counts. So when you were calculating over here, g times m1 times m2 divided by the radius squared, what you would be putting in here is the mass of the pebble for one mass, the mass of whatever amount of Earth exists below you as a sphere, and the distance between them would be the distance to the center of mass because you would treat this as a single point down here and r would be much smaller. So r would be smaller, but the mass would be much smaller too, and then you would find that the gravitational force down here would be much less than in the first case because the amount of matter that you have underneath you is much less. And again, it's the same reason. Why doesn't any of this mass count? It's because a particle standing here is going, all the mass above is going to be pulling up, and all of this mass is going to be pulling down, and this pulling up and pulling down cancel out, and so those forces mathematically can be shown to not matter. Mathematically, it's only the mass in here that's going to do anything, and you can use calculus to show that this is true. So then we'll do one last little example. If this is my final destination, and I put the pebble right in the middle of the Earth, which I can't do because the middle of the Earth is molten, but let's say I dug a tunnel all the way to the bottom, and I literally stopped right in the center of the Earth, then what would the gravitational attraction between the Earth and the pebble be right here? Fg would be exactly equal to 0. So if I could dig all the way to the center, which is molten, so I can't, but if I could, and I could stand down there, I would literally be floating like an astronaut or something down there because all the mass above would be pulling me up, all the mass below would be pulling me down, all the mass over here would be pulling me this way, and all the mass over here would be pulling this way, so my net force would be 0. So 0 gravitational force there. All right, last thing I'm going to say before we do our first problem is, of course, here's our equation. This gravitational constant I told you was determined experimentally. What do I mean by that? You build a machine where I put a known mass 1, very precisely known number of kilograms, and then I have a mass number 2, very precisely known number of kilograms, and I separate them with a very precisely known distance. Then I know all these numbers very well, and I measure the force of attraction. I measure that with a very accurate scientific apparatus. So I know the force, I know the mass, I know the distance, and then I just backwards calculate what g must be. And I do this experiment many hundreds of times for different masses, and I figure out that no matter what masses I put in there, yeah, if I put different masses, I'm going to get different forces. But when I get it all in there, I'm going to calculate the value of g, which is a constant of nature, the gravitational constant. How would you do that? There's something called a torsion balance, and I'm not going to waste my time trying to draw a great example or a great, picture of it because I'm not going to be able to. But looking down, you have some mass here, right? A known mass attached to like a rod or something. And these masses are known precisely. And how are they known exactly? That goes into experimental physics. You have to go look up exactly how they know what the masses of these things are. And then on a separate arm, what you do, which is on a pivot point right here, there's a separate arm that goes up like this. like this, and it goes down to the other side like this. And attached to the end of this arm is another mass. We're going to call it little m. Here's another mass, little m, right? And because they can measure the angle between these things, you know the distance very, very, very accurately right here. This distance r is known very accurately, and you actually measure it with a laser, actually. Because there's a laser involved, and anytime this pink one twists, then we can measure the distance between them because there's a laser bouncing off of it, and we can immediately see down to tiny millionths of a meter how much that little bar moves. Okay? And then what we can do is we can measure the force between them. We know the masses, and we can, with a laser, measure the distance, and then we can calculate g, the gravitational constant g there. That's an experimental measurement that's done, and we find out that no matter what masses we put in place, we get exactly the same universal constant called the gravitational constant. Now this g, big G, is totally different than the 9.8 meters per second. Notice that gravitational acceleration g is not a constant anyway. Near the surface of the Earth, we say it's 9.8, but if you go up to the top of a mountain, it's very slightly smaller than 9.8. If you go to another planet, then acceleration on Jupiter is different. Acceleration near the surface of the sun is different. So it's not a constant of nature at all. But this g, this capital G, 6.6, whatever it was, times 10 to the minus 11, that is a constant in the universe that we believe is constant everywhere in the universe. And so, at least according to current theories of physics. All right, now we're going to do our first quick little problem. It's not going to take very long. And here it is. Planet 1 has a mass m and orbits its star at a distance d, where it feels a gravitational pull from its star, and we're going to call that F1. So gravitational force number 1. Planet 2 has a mass 2m, and it orbits the same star at twice the distance, where it feels the gravitational pull from its star, which is called F2. So if the mass of the star is m sub s, find the ratio F2 over F1. Now right away, when students read something like this, I mean, me included when I was younger, I freaked out because there's no numbers. Where are the numbers? I mean, there's nothing here. What do I do? I've taught you the equations, but then you're like, what do I do? Well, see, so you got to get over that fear of not having numbers, right? You have to write down what you know, and you must draw a picture. And then you have to use the equations without numbers. It has to be a strength and a comfort of dealing with algebra. And you just have to sort of get over that. So let's solve it together, and we'll figure out what we're asked to do. All right? So what we have is a situation where we have a star and we have 2 planets, right? And so over here, we said the mass of the star, we're going to call it ms. That's the mass of the star. And the problem says planet 1 has a mass m right here. So I'm going to call it mass m, and it orbits the star at a distance d, right? So I don't know what m is, and I don't know what d is. So what you have to do is just put it on here from the center here. Notice to the center, we go center to center. We call that distance d, okay? Right, so we've put down everything we have so far. Now it says planet 2 has a mass 2m, and it orbits the same star at twice the distance. Twice the distance. So what we're saying is, we have another star, and we say that that one is a mass of 2 times m. So we're going to put it out here, and I'm going to make it a little bit bigger because it's twice the mass of this one. I'm going to put 2m because the mass of this one is twice the mass of this one. And it says it orbits at twice the distance. Well, if this one orbits at d, then this one is going to orbit, that's why I drew it roughly twice as far away. So what I'm going to do is I'm going to say that the distance between here all the way to here is 2 times d. So see if we've translated it. Planet 1, so I'm going to say planet 1 is right here. Planet 2 is right here. So planet 1 says, has a mass m, we have that on the board, orbits a star at a distance d, right there, and where it feels a gravitational force from its star, which we call F1. I mean, I'm not going to draw the forces here, but there's a gravitational pull on both of them. We call it F1, right? Then it says, planet 2 has a mass of 2m, which we wrote there, and it orbits the star at twice the distance, and it feels a gravitational pull F2. If the mass of the star is ms, which is what I wrote here, find the ratio F2 divided by F1. So what we want to figure out is F2 divided by F1, the ratio. In other words, how many times bigger is the force due to this interaction compared to the force due here? This one is F sub 1 right here. call that F1, and over here, this one's F2. So the force of gravity between these two is F1, the force of the gravity between these two is called F2. And we just want to find the ratio between them. No numbers other than the 2's that are in here. Now, the thing you have to do is start with what you know. What you know is the gravitational force according to Newton is G times M1 times M2 divided by R squared. That's just copied straight from the other board. All right, and we want to figure out what the ratio of these two forces are. So what we're going to do is we're going to say, well, let's calculate what this F2 force is divided by this F1 force, and see if we can figure out how many times bigger F2 is compared to F1. That's what the ratio will tell us. All right, so F2 is going to be the force between these two bodies. It's going to be the product of the masses, right? It's going to be, first of all, G times the product of the two masses, the mass of the star, and then the mass of the planet, but the mass of the planet is 2m. All right, and then over here, it's going to be divided by the distance between them squared, but the distance between them is 2d. 2d, you got to put that in parentheses squared because it's the whole distance squared, right? So that's what's going to be on the top, and then on the bottom, we have to write what's on the bottom, which is going to be the force between these two, which is going to be gravitational constant G multiplied by the product of the masses, ms, and then m is the other one here, not 2m, just single m, and then the distance between them is just single d squared, like this. Now, before we do anything else, we take a look at what we have. On the top and the bottom of this fraction, we have a g and a g, so the gravitational constants cancel. We also see that we have an ms in the top and an ms in the top here. I mean, you could flip and multiply. What you would figure out is ms on the top and ms on the bottom, but we all know that when you have a fraction divided by a fraction, whatever's in the top down here and the top up here, if it's the same thing, can cancel. And the m also is here and here. Now, do not try to cancel the d's because this is squared and you're going to get confused. So save that for later. But these are the same, these are the same, and these are the same, so I can cancel them right away. If you rather think of flip and multiply, top and bottom, you can cancel it that way if you wish. All right, so let's move on and see how much we have simplified. Here we have a 2 on the top, and that 2 is just hanging out. And then right here, we have 2d squared. The square applies to both things on the inside, so it's going to be 4d squared. 2 times 2 is 4, and then d squared. Then on the bottom, the only thing we have after these cancellations, we have a 1 over d squared, like this. All right, so now it's better, I think, to flip and multiply. We have the 2 over 4d squared. We'll change this to multiplication, and we'll flip it over. It'll be d squared on the top, and 1 on the bottom. All right, now do we have a d squared on the top and a d squared on the bottom, so the d squares can cancel. And so all I have is 2 divided by 4, which you also know is 1/2. So F2 divided by F1 is going to be equal to, when you simplify this, 1/2. All right, so what this means, when you have F2 divided by F1 is equal to 1/2, it means F2 is 1/2 times as strong as F1, right? So, I mean, think of it this way. If F2 over F1 came out to be 10, then that would mean F2 was 10 times bigger than that. If F2 divided by F1 came out to be 100, it would mean that this one was 100 times bigger. But if this divided by this comes out to be 1/2, it just means this one's 1/2 the size of that one. That's what that means. So F2, the force between this body and this body, is 1/2 times as strong as the force between this one and this one. Now, does this make sense? We have to ask ourselves. The base equation of gravity is as follows. Notice what happened. If we were to keep the mass the same, or let's keep the mass the same. Let's say that we did the same problem, but we had a mass here and an m here, but not 2m, just a single m. Same mass, just twice as far away. If you put something twice as far away, then 2d becomes squared, and what you're going to get on the bottom is a 4. And so, just as I mentioned before, if you make something twice as far away in a gravitational, everything else is held constant, then it becomes 4 times weaker on the gravitational force. 4 times weaker. But in this problem, we made it twice as far away, which should make it 4 times weaker, but at the same time we did that, we doubled the mass. So they're fighting against each other. The 2 times farther away tries to make it 4 times weaker, but doubling the mass tries to make the force 2 times stronger. Because if you double the mass, then you're going to double the force. So you have one competing idea against another. You're trying to double the force because of the mass, but you're trying to cut the force down by a factor of 4 because of the distance. And those two things competing just means that it settles on 1/2. 2 divided by 4. That's where these numbers come into play. This factor is because of doubling the mass. This factor is by doubling the distance. So in gravity, distance matters more, is what I'm trying to say. And the reason it matters more is because it's an inverse square law. So we did a whole lot in this lesson. Very important lesson. I tried to give you an overview. I tried to tell you that every force that you've ever heard of, seen, smelled, tasted, or read about is one of these 4 fundamental forces of nature according to current physics theories, right? And the strong nuclear force holds the nucleus together. The weak nuclear force is involved in radioactive decay. The electromagnetic force governs electricity, electric force, and magnetism, magnetic force, and also electromagnetic waves. And gravity is a totally separate force, which is just attractive over very long distances. And it is the absolute weakest force, not by a little bit, but by many millions of times. I think it's like, I don't even want to give you a number, but I know that it's not just a little bit, it's many millions of times weaker. The only reason we notice gravity at all is because it's attractive and it can add up over large distances. So the entire planet can pull down on me and I can feel it, right? But on a per unit basis, the gravity is much weaker than anything else you know about. Most forces that you experience in nature are electric forces. You know, any kind of friction, that's going to be electric repulsion at the molecular level down here. Any kind of pushing or pulling, any chemical reaction, any explosion, anything like that is involving chemistry, which is involving electrons, which is involving electric and magnetic forces, okay? Then we said that the form of the equation for gravity was discovered by Newton. The same force that pulls the apple off the tree also pulls the moon and all the other planets there. Now, why does the moon go round? Why doesn't it hit the ground? That's a lesson for another day. We'll talk about orbits very soon. But it is pulled towards the ground by this force here. There is a constant of nature, which we think is unchanged across the universe, and it's an inverse square law. We talked all about that. These forces are applied, the same force is applied across both bodies. The only reason I feel the force and I don't think that the Earth is feeling the force is just because the Earth is so much more massive. But in fact, the Earth is pulling on me and I am pulling on Earth with equal and opposite forces according to Newton's third law. If you have multiple forces due to multiple gravitational influences, you add the forces graphically or vectorially, which we'll do in a few problems here pretty soon. And then we said that the electric force has the exact same form as the gravitational force, which is very curious. So perhaps there's a link between electromagnetism and gravity that goes a little deeper, and that's what people are trying to figure out. We said that any extended body, like a planet, can be treated as a single point of its mass at its center of mass, and that can be shown by calculus to be equivalent. So that's what we do for all the problems. And if you start digging a hole, then eventually you're going to have only the mass that's inside of the sphere where you're standing at counts, so getting smaller and smaller. Eventually, at the very center, you have no gravitational force at all. We said you can measure the gravitational constant experimentally, and then we had our problem that we solved here. So, long lesson. What I'd like you to do is watch it a couple times. I think there's a lot of little nuggets to get out of it, right? And then follow me on to the next lesson. We'll get more practice with applying Newton's law of gravitation. Learn anything at mathandscience.com.